Actually, before I go into this topic, I want to share some excitement. So one of the things is Ian actually was just talking to me in the break that he's figured out a way to run Mplus on iPads and iPhones and things like that. So you can, if you're interested in that stuff, you can talk to him about how to run Mplus on the cloud, basically. So, and then the other idea I wanted to share is that, going back to this example with the random loadings and the original application by Herbert Marsh about doing exploratory factor analysis for multiple groups. And the idea there being that, if you do exploratory factor analysis from one group to the other, there's this measurement non-invariance, and if you do these EFAs from one group to the other, they could look different, right? Well, we don't actually have, so to actually implement this in Mplus, you could actually have EFA that has group-specific adjustments. Well, we don't have that yet, but that's somewhere probably in the future where we can have the EFA actually be done with random coefficients, basically, where the EFA parameters be random as well. But let's get back to, did you say well, Bengt? Yeah, we had a slide on that, but it's not implemented in Mplus, but someday. As we mentioned before, this three-step procedure can be done for other models. So you can have the measurement part of the model. So we can have the measurement part of the model be separated from another model. In the model, we're going to be I'm going to basically show you how you can actually do this manually. So we've implemented the two model, which is basically the distal outcome model, and the other model that we've implemented is the C on X regression. And those are done automatically by Mplus. But I'm going to give you an example here where you can estimate Y on X regression, and where C acts as a moderator of that regression. And here's that model, basically. And I'm going to show you how to manually do the three-step procedure. So we have a latent class variable C that's measured by an LCA model. And we want to actually estimate a regression, a linear regression model, a simple linear regression model. Y regressed on X, where both the intercept and the slope vary across the classes affected by the C variable. And I'm going to show you how you can actually estimate that model independently of the measurement part of C, independently of the LCA model. So we're going to use a simulated example where these are the parameter estimates we use to generate the data. Alpha 1 equals 0, and this is the intercept in the second class is 1, beta 1 equals 0.5, and beta 2 minus 0.5. Now, if you had the C variable measured perfectly with no error, that essentially is a multiple group analysis here. But because the C variable is not measured perfectly, you will be required to do this three-step procedure. And so we generate data, and then we do the step one is basically, again, it's the simple LCA model, just the measurement part of C. You just have the indicators and no auxiliary variables in the model. And in the first step, well, basically all you need to do is add this command, save data, specify a file name, and also you specify this is the option that is going to give you the posterior class probabilities for each observation, the cprop command, which will tell you basically each observation, it will tell you which, for each observation is going to give you the class membership, also in terms of probability, what's the likelihood for a particular observation to be in each class. But this option actually gives you something more. It gives you that variable n, which is the most likely class variable. And it's nothing more than just comparing the posterior probabilities for being in each of the classes and just selecting the variable that has the largest probability, basically the largest, the most likely class, just by comparing these posterior probabilities and choosing the latent class to be the variable with the largest posterior probability. And basically, this command here automatically creates that variable, the most likely class variable. And you know, this was actually not something that we've implemented in version 7. That existed basically since version 1. This was always there. We just didn't know that you can utilize it that way. So this is step 1. You estimate the LCA model. You save the most likely class variable. That's step 1. In step 2, you basically have to do a little bit of manual computation here. And what step 2 does is you have to compute the error rate of the most likely class variable. And that's basically the measurement error, and is going to be a measurement for the latent class variable, but it has an error in it. If the class separation is not perfect, the most likely class variable is not going to be a perfect measurement for the latent class variable, and it has an error. And the error is actually can be found in this table. That comes also, that's another table that actually has been always produced by Mplus, and it's, you can find it in this section, average latent class probabilities for most likely class membership by latent class. And basically what this is, if you look at the variables, if you look at the all the observations that were classified to be in class 1, they are classified with certain probability, but that probability is not always 1. So with certain probability, that observation that's classified in class 1 can also be in class 2. And so this actually tells you with what certainty we have identified the class variable. And that basically is not 0 here. It's not, if it was classified perfectly, this would be 1, 1, 0, 0. But it's not classified perfectly, and so there's a little bit of a measurement error. So you take these numbers, and you can compute them with a simple computation. So you basically take the first row, and you compute the log odds ratio, and you get these parameters, these two parameters, and those will be the parameters you need to put in the third step. So here is the input file for step 3. And again, this is the n variable, which is the most likely class variable. And when you save the data, you get the original data points. These are the class indicators. Then it's the two other variables that you're going to analyze in a regression of y on x. Then you get the class probabilities in that same file that you've saved. And then this is the most likely class variable. And you declare that class variable as nominal, right? So in Mplus, that's a way to specify a variable as being an ordered categorical, basically. And you basically run a mixture analysis model in the third step again, where C has the same number of classes as what you had in the LCA model. And now you can actually specify the auxiliary model. So you're going to use Y, X, and N. And here's the model. You basically use the same parameters that you obtain from the log odds ratio And those will be the mean parameters that specify that n is an indicator for the class variable with certain error. If n was a perfect indicator for C, these values will be fixed to 15, right? If they are fixed at 15 and this is fixed at minus 15, n will be a perfect class indicator. But because n has a measurement error in the way it measures C, it's not a perfect measurement instrument. So it has these values that are obtained from the first step procedure, the LCA estimation. And you fix this measurement error to whatever the LCA class actually estimated. So in this model estimation, because why is this even identified? We only have one indicator here for the latent class variable, but the measurement error is fixed, so these parameters are fixed, and that's why the model is actually identified. And in this model, you don't actually need to run, for example, starts. Starts is something we use to exhaust different class formation. But because n is somewhat of almost a perfect indicator, the latent class is actually extremely well identified. So it's almost like a multiple group with slight measurement error. So it's almost like a multiple group, but not quite. But you don't need to run starts in this model. You can actually just specify this indicator, which is going to almost perfectly measure the class variable, and then you specify your model, the model, and which is the model is basically that you have the linear regression of y on x, and the linear regression has different coefficients between the two classes. And then we run this model, and I'll show you the results. And these are basically the results of the three-step procedure, which you get your estimates, again, independent of the measurement part of C. So this is y on x. The true value was 0.5. You can see it's very close. The intercept, the true value was 0. It's again within the confidence limits there. In class 2, this was minus 0.5. Again, it's very close. And the intercept was 1. And, it's, again, very close. And these are the basically the parameters that were fixed here. And those were not important. But basically, you get your model estimated in step 3. And you get, again, you get an estimation, a model estimation that's independent of the measurement part of the latent class variable. And so with that, we're going to move to a new topic. And Bengt comes up on stage. Yeah? N.
Can you repeat the question, Tihomir?
How do we use N? So N is the part that makes this almost like a multiple group analysis. N is actually almost a perfect indicator of C. And that's how it's used, basically. No, that's the specification.
Wait.
N is the class indicator. Right here. So this basically statement means that the probability that n equals 1 in class 1 is 0.85. So I'm sorry, I'm going the wrong way here. There you go. So this statement right here, the fact that this intercept value, this is basically a logistic intercept, logit intercept, and what that statement means is that we specify the probability that n equals 1 when c equals 1 is 0.835. And that's basically 1 minus that. So we do allow a little bit of c and n to be different, but not by much. We don't allow that much. So again, if that was fixed at 15 here, n and c will be equal. And if that was equal to minus 15, yeah, and c will be equal in class 2 as well. This statement here basically says that probability of n equals 2 given c equals 2 is 0.89. Okay. Yeah.
It's on. If you have more than 2 classes.
Yeah, have more than 2 classes. How do you specify this? Do you aggregate amongst them, or do you specify all the permutations between the classes in the end?
Oh, you're going the wrong way.
So if you have more than 2 classes, then basically you're going to have to compute the log odds ratio. This table is going to be 3 by 3 here. And you're going to look at the log odds ratio between the first class and the last class, and then the second class and the last class. So you're going to get 2 parameters that way in class 1. And then in class 1, you're going to have to put these values right here. There will be 2 parameters for n, and you're going to use the same values that you compute from the log odds ratios. So yeah, it's slightly more complicated, but we don't have an example in that web node that has 3 classes, but it's basically the same idea that you're going to basically fix these parameters, the mean parameters for n, in a way that n is almost a perfect indicator of c, that n and c are almost identical, except you have a little bit of measurement error that comes from this table.
All right, folks, we're going to take the next hour devoted to latent transition analysis. And you will get a chance before lunch to have a question and answer session where we'll try to pull out the consequences of this new 3-step method. How far can we go with it? And I think we can have a lively discussion about the extensions that you can sit and ponder while I present the related topic of latent transition analysis. So latent transition analysis has to do with latent class analysis at several time points. And there is some interesting new development in version 7 related to that. Maybe not as sexy as this development, but nevertheless quite useful, I think. And there are 3 major new developments. One is a new Tech 15, new Tech output, which will give you transition probabilities conditional on certain background variables like treatment, control, male, female, output that you would not get in version 6. A second new feature is an LTA, latent transition analysis, transition probability calculator, where you can calculate transition probabilities for different values of a continuous or several continuous covariates. Also not possible in version 6. And finally, a specific probability parameterization to simplify input for so-called mover-stayer latent transition analysis and other models with restrictions on the transition probabilities. For the reason that the mover-stayer model has become quite popular among some people. People tend to fall in love with that model, but it's often unrequited love, unanswered love. It's hard to do, and I don't blame you because I think it's hard to do also. We have a very general modeling framework, but it is not easy to move around in, so therefore we came up with a new alternative probability parameterization. So in the next 50 minutes or so, I'm going to try to give you a feeling for how useful those three new LTA-related options in version 7 come in handy. And I'm going to give you a couple of examples. I don't know if all of you know about LTA. So the first thing you should think about is look at my hands here. Here, time point 1, time point 2. Here is latent class variable C at time 1 and C at time 2. And typically we have the same number and the same indicators, same measurement instrument at the two time points. And we want to have measurement invariance across time of those relationships between the U's and the C's. So we have that invariant. And then we study the transitions here from this thumb to this thumb. So now this picture will forever be ingrained in your mind. My thumbs. Anyway, David Kaplan, a former student of mine, did an overview of LTA modeling using an early childhood example. This is in developmental psychology. And he used Mplus to analyze the ECHLS data, ECHLS standing for Early Childhood Longitudinal Study, the kindergarten cohort, which is apparently easily accessible and publicly available because he just gave us the data. And I think we have the data here in Utrecht. And it is considering 5 dichotomous proficiency scores having to do with early reading ability. As a background variable, we're going to have a binary covariate, it's a poverty index. And his latent class analysis at each of the time points suggests 3 classes: low alphabet knowledge SSLs, early word reading, and early reading comprehension. I'm going to give this as an example of LTA just to warm you up to it. So there you have the 3 classes again. And this data set, or this analysis, has a special feature of specifying no worsening, no decline in knowledge as 0 transition probabilities. So if you look at this table here, the rows are the 3 latent classes that we look at the top in an early grade, and here in a later grade, the columns. So you have a probability of being a low alphabet knowledge person in the first grade and staying in that classification of 33%. 33% don't move away from that low reading status, but 66% move from status 1 into status 2 across these 2 grades. And almost 2% actually move all the way to the highest proficiency. Likewise, those who start in the middle class, early word reading, 65% of staying there, but 35% of moving on. Here is the 0 restrictions that we say. We say that starting in class 2, you don't go down to, you have 0 probability of going down to class 1. Likewise, starting in class 3, you have 0 probability of going down to classes 1 or 2. It's just a specific structure that Kaplan was interested in capturing. It's not typical for LTA, but it's a specific application. And furthermore, relating to the dichotomous covariate, it's poverty. You are either scored as coming from a family of poverty or not. Poverty or not, I should say. Here you have the transition tables once again, but now you have them for each of the 2 poverty statuses. So those who are in the low poverty, that is, they're not in the poverty class, or category rather, and they have a fairly high probability of transitioning upwards, whereas those who are in the poverty category have a much lower probability of transitioning upwards in a positive direction. So you're interested in these transition probabilities between my right thumb and the left thumb, and you want to let those transition probabilities vary across different kinds of background characteristics, in this case, the dichotomous observed poverty variable. A second example that we're going to play off of is my former student Karen Nyland's dissertation study. And it has to do with peer victimization, so bullying. And ladies and gentlemen, it just so happens that we have the world's expert on bullying matters in the room here. Will Don Olveos please raise his hand? He has interventions going on all around the world, it seems, including the U.S. This is a study out of L.A. Sandra Graham and Jana, I forget her last name. Anyway, they have a study in L.A. Schools, ethnically quite diverse public middle schools, 48% Latino, minority Caucasian. 2,000 people. And the sample size becomes quite important in LTA because you need large samples to have stability in the transition estimates. And I don't think everybody's aware of that because often in customer support with Mplus, we get questions of how do I do transition analysis and mover-stayer analysis for a sample of 200. Well, you can get decent estimates, but you have no idea what the significances are in terms of differences in transitions for, say, low poverty and high poverty. You need a sample of about 2,000. 6 binary items of this kind being bullied in various different ways. There's apparently a peer victimization scale that is commonly used in this field. Here's what it looks like. The idea is one of movers and stayers. So you have 3 classes, students who are victimized, students who are sometimes victimized, some students who are not victimized. And we studied this in grades 6 through grade 8. And it looks like the victimized percentages go down across the grades, and therefore the non-victimized goes up across the grades. So we have 2 categories of individuals, movers and stayers. And the interesting thing is that that is a latent variable. It's not like poverty, which was observed in the Kaplan study. It's a latent categorical variable, which plays a role in the model very similar to second-order factor analysis. You have one level of first-order factors, and then they are caused by a second level of factors. Same thing here. You have the latent class variables at time 1 and time 2, but behind them you have another latent class variable which characterizes you as a mover or stayer in the following sense. Say that you consider grade 6 transitions to grade 7. For movers, you have a probability here of transitioning from the victimized class to the better class of only sometimes victimized, 0.29, 0.45 here. And pretty much the same thing in grade 8, transitioning from grade 7 to grade 8, you have a fairly healthy probability of transitioning out of the victimized class. But there's a group of stayers who don't tend to move from their statuses. So the probability of, if you start out as victimized, that's the first row here, the probability is 1 that you stay victimized in grade 7 and 0 that you transition. Same thing for the next transition. So you have this, what we statisticians call an identity matrix here for transition matrix. This is pre-specified. This is like CFA, fixed, specified. And of course, you immediately think BSIM, right? Mm-hmm. Good. But we haven't done it yet, so you can do it. And what the idea of the analysis is to try to tease out how many people are stayers and how many people are movers. And later on, we're going to try to have explanatory variables for who ends up in which of these 2 second-order classes. Just 2 examples to start us off. Now for the first novelty, Tech 15 rather, we're going to consider an observed categorical covariate. So we're going to go, yes?
Like a very specific moving pattern.
So you would loosen up these zeros for some of the rows, you mean?
For example?
Yeah. And actually, you don't have to have any structure here at all. You can do this analysis totally exploratory. It could be a latent class variable which just gets formed automatically in an exploratory way by the maximum likelihood estimation. That's quite possible. But the typical case and the easier case to handle is when you pre-specify this as a very structured. But
Can you specify this identity matrix as an input? So can I
Yes.
specify specific patterns like the second row, all the values have to be 1 or something like that, based on theory, of course, as well?
yeah, well, you can only each row has to add up to 1.
Yeah.
But you're right. You can have estimate this and this while you have zeros here and zeros there, but not exact zeros here. Absolutely possible. Yeah, there are all kinds of variations there on that theme. And in fact, to decide between these models, you should use the Bayesian information criterion, the BIC. Bayesian, despite the fact that we do ML. All right. Back to the story. We are going to deal with covariates that are continuous and categorical. We're going to deal with covariates that are observed versus latent, just to keep you informed in the field here. What I'm talking about now is observed covariates, not like mover stayers, which is unobserved. And we're talking about a binary dichotomous covariate. A very good way of dealing with binary observed covariates is through known class. Known class is a mixture concept where you do essentially a multiple group analysis by saying that you have a latent class variable that's perfectly observed. That's what known class is. And essentially that's what Tihomir showed when he fixed those n intercept values. New feature in version 7 is Tech 15, conditional probabilities for C on C type of relationship, where C on C, by that I mean, in this case, the latent class variables at each time point rest on the known class C down here, which is could be the poverty variable, for instance. Here is how you can depict it, and here is how it will be depicted in the new user's guide. In the new user's guide, we're actually modifying our example 8.13, which was the first LTA example. Turned out that that was too complex and not general enough, in a sense, in both senses, at the same time, I should say. It was specific to an Moyart analysis, another Dutch person, a good old friend of mine. But it didn't reflect a general type of LTA, and therefore people went astray a little bit in applying it. Also, it was limited to 2 latent classes, and that doesn't generalize easily to 3. 3 is the pedagogical number. We should remember that, Tihomir, when we finish the Web Note 15. Stay with 3 instead of 2. So here's how we are changing it. You have an observed covariate X, say, typical notation, where we put the circle in a square to denote that that's a known binary latent class variable. So it's a latent class variable with 2 categories. So poverty would be a perfect example of that. Let me say that poverty influences the probability of class membership at time 1 and at time 2. But also poverty influences the relationship between C2 and C1. So that broken arrow says that essentially the slope here varies across the 2 known classes. Here is the input for that, corresponding to the picture. Now we get good use of 2 screens. You have a known class variable CG, and it's determined by the observed variable G, which sits up in the data set. That's the last variable in the data. So CG becomes perfectly observed. And in the overall part of the mixture modeling, you say C1 and C2 on CG. That's these 2 arrows. And the C2 on C1 is relegated to the model CG specific classes. So you have a C2 on C1 in CG class 1 and a C2 on C1 in CG class 2. So these 2 things, if you want to circle that and scribble in your notes, they correspond to the broken arrow. that the relationship between the two major C's is different for the two different classes of X, which is G, which is CG. And then you have the measurement model. Here we have the three classes for C, for C1 rather, three classes for C1, and we label the thresholds, and those labels come back for model C2. Same numbers, which says then this slide and the previous slide specifies measurement invariance across time, which is a standard approach. If you have the same measurement instrument, you don't have to have measurement invariance. You don't have to have the same measurement instrument, but this is the standard approach. So this is a lot for those who've never done latent transition analysis, but we are here in the advanced day, aren't we? A quick review of the standard Mplus parameterization for latent transition analysis is based on a logistic regression type of parameterization. We call loaded parameterization for the relationship between latent class variables. So you have C2 at time, that's the C at time 2. C1 is the C at time 1. And you consider each row for the those in the C1 equals 1 class. Here are the logits that determine the probabilities of transitioning or not between the two time points. So each row shows the coefficients for a multinomial logistic regression of C2 on C1 with the last C2 class as a reference class. So C2 is the dependent variable, C1 is the independent variable, and we do a multinomial logistic regression of the nominal C2 variable onto C1. All of this is in chapter 14 in the user's guide. Now, when Kaplan wanted to have lower triangular probabilities of 0 here, he therefore has to choose these logits so that the corresponding probabilities become 0. A 0 probability is a very low logit, like minus 15. So he fixes the A1 and A2 and B12 coefficients to logit values minus 15. So this would be all very low logit values corresponding to 0 probabilities, whereas the other parameters up here are estimated. This is just repeating standard LTA. And you have the kindergarten, the Kaplan analysis on your right screen here, dpanalytic.dat, and you have all the names, and you work with 2 time points here as an illustration. You have type equals mixture. You do a healthy number of starts, and you use an 8-processor machine that is mine. And here's how you fix the lower triangular transition probabilities at 0 in the standard loaded parameterization. Here are the intercepts, the A1 and A2 in the left screen, fixed at minus 15. And then you have the B coefficient, B12, fixed at minus 15 here. And a little known fact is that you may want to compensate for those minus 15 for the free parameters by adding a 15 to start at a loaded start of neutral start of 0. Otherwise, you may end up in local maxima. I don't want to talk too much about this because it's version 6. I want to move to version 7 stuff. Here's the measurement invariance. And it gives this latent transition table that we talked about. These minus 15s translate into estimated transition probabilities of zeros. Instead, I'm going to go to what's new in version 7, the poverty covariate, the observed covariate as known class. So we are taking Kaplan's example here, the first example we talked about, and the Eccles K data. Known class. Here is the poverty variable. And we have C1 on that poverty variable. And for model CP, the CP is the poverty known class variable. We have C2 on C1 and C2 on C1 minus 15. Oh, no, sorry, no, it's not 15. These are the compensating ones. The minus 15s are up here. And you have a C2 on C1, that's specific to the second CP class. So that's just as how it's been so far in the logistic parameterization. But what you get here now is the Tech 15 output. You get these conditional probabilities, and you have them on the two screens following each other. This is Tech 15 output. So for instance, you have the transition between C1 equals 1 and C2 equals 1 at CP, the poverty 1 category here. And then over here, you have it at the poverty 2 category. So that is information that you would not get in the usual version 6 analysis. It would be hard to tease out. And that gives you the two transition tables that I showed you earlier on for poverty 0 category and poverty 1 category. So that's Tech 15, which is useful, again, when you have a categorical covariate, not continuous covariate. Now, what about the case of a continuous covariate? Well, we have tried to make that easier to understand by writing a web note 13, transition probability influenced by covariates, and that's continuous covariates. It's been then expanded to being able to calculate transition probabilities for each distinct value of the covariates using the so-called LTA calculator. And that leads to, that should be seen in the following context. We are talking about interest in transition probabilities being influenced by covariates, in this case continuous covariates, before it was categorical ones. And there are actually two ways of displaying that interaction. It is an interaction between the covariate and the first latent class variable. And it can be drawn in this way, or as shown on the right-hand screen. We started off with this, saying that for the different poverty class categories, the relationship between C1 and C2 was different. Same thing, analogously, we can say that for different C1 classes, the relationship between X and C2 is different. In both cases, it's an interaction between the X and the C1, X and the C1, a product. Very much akin to the loop example that I showed you yesterday. An interaction is a moderation. A moderation can be expressed two ways. It's a symmetric relationship, and you choose the one that makes substantively most sense. Which of the two variables in the interaction moderates the other's relationship is up to the substantive researcher. Anyway, focusing on this interpretation here, this version, which is the second version here, you can then specify how the relationship between the two C variables vary across the values of X. And this is in our web note, and it's called parameterization 2. So you say here in the overall, C1 on X, C2 on C1, but then C2 on X is specific to the C1 classes, in this case 3 classes. So you say C2 on X 3 times. So 3 different kinds of regressions of C2 on X, depending on the class variable for C1. Here is the Lodiet parameterization that underlies this specification. So far, it's version 6. It may be new to you, but it has been there. And it's done this way. Now, poverty sits up in the use variable list here. Poverty is the observed covariate. We're going to do an analysis that would be useful also if poverty was continuous. It doesn't matter if it's continuous or binary here. The approach we're going to show you is for a totally general kind of covariate. So poverty is no longer on the latent class list. It is an X variable, so to speak. And you have then in the with the Eccles example, you say you follow the parameterization 2's style, and again parameterization 2 is described in web note 13. And you say C1 on poverty, just like C1 on X, top left. And then you do C2 on poverty relationship in C1 specific model part to get the interaction. So you do the C2 on poverty down here, corresponding to the statement top left out here. Now Kaplan, of course, has a further complication of these zero probabilities for declining in knowledge, which complicates it a little bit. But I want to give you these slides. You don't have time to sink into them, obviously, now. But you have them here, and you can study them when you do the analysis. But I want to get to the point of this, and that is the new LTA calculator. Louder, please. So we want to calculate the transition probabilities here for any kind of value of X. To do that, you look top left here. Top left, it says Mplus LTA calculator. So you can try that this afternoon. It's in that preliminary version 7. And up comes a covariate value menu where you can name the covariates, can be many of them, and set the values of them down here. And that shows up this window. In this case, we use a 0 here for the poverty. And what comes out is estimated conditional probabilities for any kind of value here. It doesn't have to be the 1, 0, which would be relevant for this dichotomous covariate, but it could be age, for instance. You can plug in different age values. And out comes the transition probability of C2 statuses as a function of C1 statuses. Very useful. That's a fine collaboration between statistical programming and parser programming. So Tihomir and Twee, as very often, talk to each other. That was the second novelty. Do you remember what the first one was? Tech 15. What was Tech 15? Oh, that was just conditional transition probabilities when you have a binary observed covariate. Second novelty, you haven't forgotten it yet, right? Was the LTA calculated for a continuous covariate. And now the third and final innovation. And we're doing well on time. Transition analysis in probability parameterization. And it's an innovation that came from trying to help so many people do latent transition analysis, particularly mover-stayer modeling, and getting stuck on it and not understanding how to set up the logit parameterization. And as you've seen and sort of felt when I went through it quickly here, it can get complicated with these -15s and +15s. So Tihomir and I launched into this last fall, I think it was. And LTA models that do not, it's suitable particularly for LTA models that do not have continuous axes. They can be more conveniently specified using this new probability parameterization. And so this will be part of the new Tech 14 description in the user's guide. So again, you look at this C1, C2 transition table. It's not expressed in logits anymore. It's expressed in probabilities. And once again, you look at it row by row. The row probabilities have to sum to 1. So, I'm sorry, what? It is not 0 in a sense. It is a reference category. That is, the only probabilities, the probability parameters are for the first two, because we know that the last probability has to be 1 minus the sum of the two. So it's not that the probability is 0, it's just that you don't have a parameter there. You don't need that parameter. So probabilities in each row add to 1, and the last C2 class is not mentioned. Maybe we should have left it blank here, more pedagogically. The P parameters are referred to using on, so this C2 on C1, right? And the latent class variable C1, which is the independent variable, it has further probability parameters in brackets, C1 number 1, C1 number 2. And those are sort of like intercept or mean parameters for the independent or predictor variable, whereas intercept parameters are not included for C2. They're not needed. Probability of C2, if you remember the elementary probability of C2 is the probability of C2 given C1 times the probability of C1 adding up over the different C1 possibility. That's a marginal probability of C2, that you don't need any intercept-like parameters. And here then a transition probability can be conveniently fixed at 1 or 0 using the probabilities directly. So there would be these three probabilities that you would fix to 0 if you are interested in Kaplan's model where you don't get worse. And those three are 0, and that is 0, and these two diagonals are 1 if you're interested in the identity matrix of the stayers. So it's a more direct translation of your hypothesis into parameters of the model that you accomplish by this. So one could go through all the previous loaded parameterization analysis that we showed and do it in the probability parameterization. We're not going to do all of those now, but you have the opportunity this afternoon. And I think the example for the exercises this afternoon, Rens, is it only the Kaplan data, or did you bring? You had an alcohol data set instead, right?
Yeah. We now have to look at data because we prepared the exercise on the
Okay. So, and that's well described in the exercises for day 2, right? Yeah. Okay. And I don't know anything about that data, but it will be interesting to see how you approach it. So now, slide 83 and 4. We are in the Kaplan example, and we are interested in this model. And we are going to use a probability parameterization. Let's see, why does it say logistic parameterization there? Well, I guess my idea was to first talk about the probability parameterization for Kaplan's example and then go on. That's how it flows. So in the Kaplan example, we consider 2 time points, C1 and C2, and we say parameterization equal probability. And now the 0 lower triangular transition probabilities are specified as 0. So these are 0 probabilities. For C2 number 1, the first column, on C1 number 2 to C1 number 3, there's 0. These are the lower triangular probabilities saying that you don't get worse from grade to grade in reading achievement. So it's fairly simple, more straightforward to deal with in that parameterization. It goes more straight from your theory to your model specification. That was what I wanted to say there. Now we move to Nyland's example. Kaplan is done. Kaplan was the 0 transition probabilities. Nyland's had to do with the mover-stayer model. And we are therefore first looking at the logistic parameterization, the messy one, and then we go to the probability parameterization. So in the logistic parameterization, we draw the diagram like this. And here is the mover-stayer unobserved dichotomous covariate, influencing the probabilities at the 2 time points, but most importantly, having the broken arrow influencing the relationship between C2 and C1 across time. We actually, that's quite complicated in the logistic parameterization, and we felt that we had to write a frequently asked question FAQ, LTA with mover-stayers, which uses the regular loaded parameterization, which is complex for mover-stayer. Actually, it took me a while to write that, and I had to ask Tihomir several times to not get lost. And every time I reread it, I have to take time to sink into it, which means that it should be simplified. If I have a problem doing that right off the bat, then they should be simplified. So, but I will show it to you first here for the nylon example, just so you have it complete, because it's a nice example, covariates and all. So here's the bullying example. No covariates in this case, just illustrating mover-stayer LTA in the classic Mplus logistic parameterization, as it were, up to move to version 6. C2 is the mover-stayer latent class variable. The first class of C is the mover class, second is the stayer class. And then you have 3 time points, which are the time-specific latent class variables. And you relate all of the latent class variables to C for movers. And you do the same thing, and those are free parameters to be estimated. And you relate C2 and C3 to C for the stayer class. And you have to start, the problem with the logistic parameterization is that you have to start specifying stayer class specific parameters already in the overall, in the intercepts being minus 15 here. And that is what causes the problem, I think, in the difficulty, because that overall specification has to be combined with the class-specific specification in a cumbersome way. But you have it here. You can also have covariates, which are used in Nylon's dissertation but not used in this analysis. Here's how you would specify it. I just want to give you that so you have complete notes on how to deal with mover-stayer if you want to do it in logistic parameterization. I'm not going to talk about the measurement part. Instead, then, now let's move away from that somewhat messy type of logistic parameterization specification for mover-stayer to the third novelty in version 7. Probability parameterization. It shines, that new parameterization shines in the mover-stayer context. That's where you really need it. And here's how you would draw it. And this would be a new user's guide example as well. So you have, say, 3 time points to make it general. And really, I think when you deal with mover-stayer, you should have more than 2 time points. In fact, somebody should write a paper on the identification issues with mover-stayer. How many indicators do you need per latent class variable? How many latent classes can you handle? Can you identify related to the 2 mover-stayer classes here? I think it's somewhat unknown at this time. Here I have 5 dichotomous indicators at each of 3 time points. And we're interested in the transitions from time point 1 to 2, from 2 to 3. And we're saying that mover-stayers influence those transitions this way with the broken arrows. So we're going to try to specify that in the probability parameterization. So we have the model on the left and the input on the right. Parameterization equals probability. And what we do is slightly different than in logistic parameterization. In the overall part of the model, we only relate C1 to C. That is this thing, C1 to C. In the logistic parameterization, we also talked about C2 on C and C3 on C, but that's not relevant in the probability parameterization. So it makes it very easy. You don't have something in the overall that then has to be combined with something in the mover-stayer specific classes. So here's how it goes. C1 on C is all you say. And then for the mover class, you say C2 on C1. That's this relationship. And C3 on C2. That's this relationship. And for the stayer class, you want to specify that identity matrix, 1s and 0s. And you see them here. 1 here, 0 there, 0 here, 1 there, 0 here, 0 there. You just don't specify the last column. Otherwise, this would be a complete identity matrix. And so these are probabilities now, not logits that has to be translated to probabilities, but they are probabilities. Here you do it for C2 on C1. That is this relationship. Excuse me. And here you do it for C3 on C2. Same identity matrix for the stayer class. Over here is what we talk about. So you have an overall part and a model C, the mover stayer class specific part, which has two classes. Movers, freely estimated transition probabilities. Stayers, totally fixed. But in line with the Ren's questioning, these can be free as well, totally free if you want to. And looks like that's identified in many cases, at least, if you have enough indicators. And all kinds of variations on this theme where some rows have zeros in it and some rows don't. Measurement part as before. Much, much simpler if you compare these slides, go back and forth. So if you want to do mover-stayer modeling, use the probability parameterization. But as always, we're never satisfied totally. Because as you noted, there was one little slippage here. And that was that this is not possible when you have continuous covariates. We haven't figured out yet, or maybe it's not even possible, to express the model in probability parameters when you have continuous covariates. Of course, not all variables are categorical. We're working here like we have an unobserved frequency table. And there you can work with probability parameterization. So we're not quite done, in my view. This is good, but not quite done. We could take it one step further and have the model specified in keep the idea of a simple specification, but not necessarily do it with probability parameters. This means we have to bring in Linda. So, but she's been too busy lately. So maybe down the road we can do a simpler mover-stayer analysis that doesn't restrict itself to categorical covariates, but can be done with continuous as well. But we have come a long way with these three innovations. Here is the next slide, which I wanted to give you as a little enticement. Who has done this kind of analysis on this slide? What does this slide tell you? Does it speak to you? Well, this is the mover-stayer model for 2 time points only to fit it nicely on this page. But once you have found that there's a certain percentage of your population that are stayers, that could imply a problem. People who keep being bullied from grade to grade, or people who don't develop in their reading from grade to grade, or in any other way stay in the same undesirable class, you want to know who they are, and you want to know what predicts their class membership. Or, so this could be a background variable like gender or age observed, or it could be an intervention. Here's your treatment control variable where you try to influence people, try to make for a smaller probability of being a stayer and a higher probability of being a mover. So this could be a very important link here to estimate. So now we've gone several layers down. Here's layer 1, it's observed. Layer 2, unobserved. Layer 3, unobserved. Layer 4, observed. Pretty wild, but it's doable. Yeah. And here's the setup for it. I did this for an example of ethnicity. So this variable here was an observed X variable. It's a nominal variable, different ethnic groups, which I can then, of course, turn into known class because it's categorical, observed. So I have CG is my known class variable corresponding to ethnicity 0 through 4. So 5 different ethnicities. And I do a mixture modeling. Actually, I throw in a complex analysis here that is correcting standard errors for cluster sampling. or weights. I can't remember which one it was. And probability parameterization. And in the overall model, I do C on CG, the known classes. That's this relationship. So C on CG, you can write a little note here. Footnote 1. And footnote 1 goes with this relationship. And then, so that's the new line. And then the old line, C1 on C, which is this relationship. And then you have to deal with the broken arrow. And the broken arrow comes in the model C specific, which is just etc. now, same as on previous slides. I just wanted to show you how one would deal with a nominal. How do you portray, how do you explicate and report results of a nominal ethnicity, say, variable, X influencing this latent class variable C? Well, when you have categorical variables, it's convenient to work with log odds and odds, or log odds ratio and odds ratios. So you have here the new parameters in model constraint defined as log odds ratio 2 through 5. Log of ratio of odds of being mover versus stayers for the groups. So you have a log odds for ethnicity 1 versus 0, which is the reference ethnicity category, 2 versus 0, 3 versus 0, 4 versus 0. And by standard definitions, the log odds are these ratios, a ratio in the numerator divided by a ratio in the denominator. And these B's are the coefficients, the low-digit coefficients sitting up here. So then you can report these log odds, or take e to the power of them and get the odds ratios, and you get something substantively meaningful to talk about. That's it, folks. I propose that, Tihomir, do you want to take 10 minutes on this? Can you do it in 10 minutes?
Yeah.
You promise? Okay. So we can have a discussion about the 3-step a little bit more, from 10 to 12 to 12, and then beat the lunch crowd anyway.
All right, we're going to throw one more mixture idea at you, and it's described in this paper, which is proceedings of the Joint Statistical Meeting. It's so the idea here is to talk about some non-independence between indicator variables in latent class analysis. This modeling idea, for now, it works only with binary variables, so we have not been able to, so far, to actually generalize this to ordered polynomous variables. This methodology is not new to version 7. Actually, it came out in 6.1 based on our improvements on the estimation of the correlation metrics. So right now, Mplus, I believe, has the best algorithm actually for estimating correlation matrices with Bayesian estimator. I actually don't think that there is another program that can do it at all, but we actually think we have the best algorithm. It's not even, it's better than all the published algorithms that are out there for estimating correlation metrics. Actually, funny thing is, right, why is it so hard to estimate correlation matrices, tetrachloric correlation matrices? But it actually is, it was a big problem for us for a long time. And anyway, in 6.1, we released the best algorithm we could think, and that was a kind of a breakthrough in this area, in the latent class analysis area, as well as imputation with categorical variables, multiple imputation with categorical variables. But let's focus on this generalization of latent class analysis here. So just to review, you have binary indicators, Y's, and the main idea behind the latent class analysis is that given the latent class variable, all the indicators are independent, right? So all the correlation between between the binary indicators go through the latent class C. So given the latent class C, all these variables are independent. That's basically what this description says right here. Another way to actually express the latent class analysis model is through underlying normal variables. So for each binary variable, there exists a normally distributed random variable, which is basically cut at 0 if the underlying variable is greater than 0, then y is 1, and if it's less than 0, it's y, the observed value is 0. So that's kind of this is basically the basic probit equation basically here. And, but you can think of this as behind each binary indicator there is an underlying latent variable y, which is normally distributed and has variance of 1 and two different means in the two classes. If you have two classes, and that's basically, this mean is minus the threshold value. That's a standard way of expressing latent class analysis in terms of underlying normal variables. And what we're going to talk about here is this simple generalization that if you actually look at the joint distribution of these underlying normal variables, the latent class assumption says that they are uncorrelated. And we are actually going to, instead of uncorrelated, we're going to generalize the latent class model and allow these underlying normal variables to be actually correlated through a general correlation matrix. So if this joint multivariate distribution has an identity correlation matrix here, then we get the standard latent class analysis model, but you can have a general latent class, general tetrachloric correlation matrix estimated within the latent class analysis. So I remember this maybe 2 years ago, Bengt was questioning me, how can this be even identified, right? Because, you know, that's what the C variable is for, to take care of all the correlations, right? How can you even introduce correlations here? And the answer is that, yeah, it's identified. The most unrestricted tetrachloric correlation matrix is identifiable. In general, that's not what I'm talking about here. I'm talking about what I'm going to be focusing on is application of the BSEM methodology to latent class analysis rather than this unrestricted tetrachloric correlation matrix. But if you have a sufficient number of indicators and sufficient sample size, you can actually estimate a completely unrestricted tetrachloric correlation matrix within each class and still have a latent class analysis model. So it is an identified model. But what we're going to do here is, instead of talking about this unrestricted model, focus on the BSEM methodology. And what the BSEM methodology does is formalize a belief, a substantive belief. And the substantive belief here that we're going to focus on is the fact that in principle, we believe that the indicator variables are conditionally independent given the class variable. But that belief, you know, it's again approximate belief, right? When you're constructing a model, you know, you basically want to really say that they're approximately independent. You know, this is a perfect world when they're completely independent. So you want to be able to allow a little bit of imperfection in your measurement model. What happens if you know, with the standard LCA model, if you keep on pressing this perfectionism and insist on independence of the latent class indicator models, what happens is that you're going to get spurious classes. And so that spurious class problem, where you get many classes that you cannot interpret, but, you know, if you consider what the Bayesian information criteria does, when you keep on estimating more and more classes, you know, you keep getting more and more classes, basically, in the Bayesian information criteria gets lower, and to the point where you cannot interpret these classes anymore. They become too small. They chase, you know, some outlier observations, and that methodology that I'm presenting here is a resolution of that. So consider this simple example. We have 6 binary indicators, thresholds are plus minus 1, large sample size, and we have actually 2 classes in this model. We generate the data with 2 classes, but we have 2 indicator variables that are correlated beyond the C class, beyond the latent variable. So if you estimate LCA based on independence assumption, what BIC is going to give you is this red number here, meaning 3 classes. So it actually did produce a spurious class. The fact that there wasn't an accounted correlation from the LCA model, you have a little bit of extra correlation between the indicator variables, that gives you a spurious class. Now, if you account for the correlation, then you just get, as expected, the 2-class solution. So, and this is basically how you do that. So this is an example of exploratory LCA. An exploratory LCA, what we call exploratory LCA, is basically where you include the correlations between the indicator variables within each class. However, we're not really very interested in completely unrestricted model. What we are more interested in is the B-same idea, where we say that these are free parameters, but they're approximately 0. We want a model that's going to estimate, that's going to be almost like an LCA model, but have a little bit of a wiggle room for these correlations to be away from 0. And this is basically how you specify that. So these are the correlation parameters. And in order to make them near 0, you specify this prior, which is inverse Wishart prior. These are correlation matrices, and that's how you specify priors for correlation matrices. Inverse Wishart distribution with mean 0. So the wiggle room is centered around 0. And this second parameter here is the degrees of freedom in the Wishart distribution. And that basically tells you how big the wiggle room is. If you want to have a very tight and tiny small wiggle room, you basically make that degree of freedom large. And if you want to make it bigger, if you want to put bigger wiggle room, then you have to make it smaller. The degrees of freedom gets smaller. And just to give you an approximate where this comes from, the inverse Wishart distribution is essentially, you take random samples, normal random samples, and you compute the correlation matrix that you get from these normal random samples. And the more, this basically corresponds to how many sample points you get in your data. So essentially, the degrees of freedom is the same as the number of observations you take to construct the correlation matrix. If you take, thousands of observations, the correlation matrix is going to be very, very well defined. So the posterior distribution is essentially going to have very little wiggle room, and the correlations are going to be exactly 0. So, but anyway, so these degrees of freedom is basically the parameter that allows you to control the wiggle room. And if you would like to start very safe, and want to be really close to the LCA analysis, you're going to put here about 100, say, and that when you put 100, very little wiggle room, you're going to essentially be estimating, with the Bayesian estimator, you're going to be estimating standard LCA model. And you gradually decrease this, and you evaluate if any of the correlations are going to be pushed out of 0 and become significant. Okay, well, just show you the results of this example. So this is a classic example from Q and Kuttner. And you can actually do this with maximum likelihood, but when you have correlations in this latent class analysis, every correlation actually takes one dimension of numerical integration. So it's very limited methodology, but that's what Q and Kuttner did back in 1996. And now with this new methodology, first of all, it's automatic. You don't need to worry about it, just basic specification about wherever the correlation is going to come out, you're going to see it. You don't need to go in Tech 10. That's what we used to do with this old methodology. You have to go in Tech 10, see misspecifications and misfits in the model with each bivariate distribution between the bivariate indicators. And now you don't have to do that. This is very automatic. Whatever you need is going to come out. And here the results of that particular example, they had only one correlation between 2 of the indicator variables. These are the results here. none of this was significant in class 1. In class 2, you just have one significant correlation. And the confidence interval doesn't include 0. And that's exactly what the Q-Kettner analysis also, what they published. And basically, if you include that correlation, you get exactly the same results as